Assalamu alaikum. This is lecture 11 on digital control system. We're discussing chapter 3, Z-plane analysis of discrete time control systems. This is the second class on article 3.5, pulse transfer function. We already have seen how to figure out the pulse transfer function and how to take the advantage of starred Laplace transformation in obtaining pulse transfer function. So far, we have covered up to the example 3.6. Now let us start with the pulse transfer function of closed loop system. So different kinds of closed loop systems are available. Closed loop systems, the types, different types based basically on the fact that we can have the sampler in different locations. So you can figure those in table 3.1, and the corresponding pulse transfer function is also given. Those you have to try with one or a few of them so that in the exam you can easily cope up those. So here we'll try to show one. This is recently the Microsoft whiteboard has been changed. I think this is because of the fact that we have now authentic version of Office 367, 360. So that is why we have to go through a slight change here and there. So it is not the one that we are familiar with previously. The previous one was a lot. I was comfortable with that one a lot. So leaving means adjusting. So let's start with this one. So this is our input RS. Then we have our error signal, which is the subtraction from the input to the reference input of the reference. From that one, we have to actually subtract the feedback that we are getting from the output through the transfer function h of s. Now this is the sampler. We have del t. Now, on the outside of the sampler, we have the starred error signal ES. Now, how can we have the equivalent system of this one, or equivalent transfer function of this particular system? So again, the idea is very simple. Just write the equation as they are. ES, the output is basically the reference. The error is basically the reference minus the feedback of the output. What is our output? CS is basically the transfer function G of S is been multiplied with the starred error. So E star S. Now again, what is E error? Error can, in the error you have C here. So we can easily replace the value of C from here to here. And then we can have our error equal to RS minus H of S, G of S, and E star of S. Now, in some portion of the equation we have star, in some portion we don't have it, and under the circumstance, the solution is taking the starred Laplace transformation. So, starred Laplace transformation. So if we take it, we know that the simple parameter will be simply starred, and complications will be arising whenever you have two grouped together, like here, G and H. So I have to write that as a GHS. So After start conversion, it will be GH star S, then E star S. We've seen that thing in the last class. So what we have now is just take common of the ES from the both side. So E star S 1 plus GH star S equal to your R star S. Okay, so for the simplification, E star S equal to R star S by 1 plus GH star S. What we are interested about the output CS. So output CS, the equation that we already had is CS equal to GS E star S. So here again you have to take star Laplace transformation that will give us C star S. This is simpler. G star S, E star S. Now you have used E star S, so you can just replace the E star S into that equation. So that will give us C star S equal to G star S to R star S divided by 1 plus GH star S. Okay, so now just you have the star transformation, you can easily convert it to the Z transformation. So Z transformation should lead us to CZ equal to GZ RZ by 1 plus GHZ. So we are interested with the pulse transfer function, that is ratio of output to the input. So CZ by RZ, which is a pulse transfer function, is GZ by 1 plus GHZ. So this is true for this particular configuration where your sampler is just before the function, transfer function G of S. So based on different kind of, based on the different location of your sampler, you can have different one. As we already said, you can have those combinations in table 3.1. So have a look at that one and try to practice a few of them. Next is our pulse transfer function of a digital controller. So pulse transfer function of a digital controller. Okay, so how to do that? So basically the relation, the digital controller's pulse transfer function can be obtained from the required input-output characteristics of the digital controller. So if you know what is the characteristic of the output and you know the characteristic of the input, so these two parameters known, so based on that we can easily find the relation what is inside the box or basically D, G, D, Z. So let's see, say that our input here is having error signal EK or EKT based on sequence or the time step, and the output is MK. So now if these two are known and you can have the characteristic corresponding to that one, so output characteristic MK plus A1 MK minus 1 delayed 1 plus A2 MK minus 2, and it goes up to say we have n the number of samples AN, m k minus n. And the input, which is error, is b0 e k plus b1 e k minus 1 plus goes on up to say bn e k minus n. So how can I find out the GDZ? So we can easily, because there are sequences and samples at different time sample, or if it is a digital signal, just a sequence of numbers. So in that case, you can easily figure out the Z transformation. So Z transformation. Okay, so Z transformation lead us mz plus a1. Delay is by what sample? So Z to the power minus 1 mz plus a2 Z to the power minus 2 mz goes out to an z to the power minus n mz capital equal to b0 ez plus b1 z to the power minus 1 ez and goes on up to bn z to the power minus n z. Now we can easily take one of the mn is ez, mz and ez, and just tweak a bit. So what we are going to get 1 plus a1 z inverse plus a2 z to the power minus 2 goes up to an z to the power minus n mz equal to bz plus b1 z inverse plus goes up to bn z to the power minus n is. We know that output relation or the pulse transfer function is basically the relation between the output and the input. So basically we have to have mz by ez, and which is nothing but the coefficients, the ratio of the coefficients. So this is your b0 plus b1 z inverse goes up to bn z to the power minus n divided by 1 plus a1 z to the power minus 1 plus goes up to an z to the power minus n, and which is nothing but your GDZ. So this is how we can find out the pulse transfer function of a digital controller based on their input and output characteristic. Say we have a control system, digital control system of pattern, something like this. This is sample and hold. Then you have digital controller. Then you have zero order hold. Then you have the plant itself. And finally, the feedback, unity feedback. So sampler and ADC. Then you have digital controller. Then you have zero order hold with DSC, digital to analog control. Then you have plant. Okay, so this is your input RT. This is your output CT. Now monitor carefully. This is where the signal is analog. This is where the signal is discrete. The output is also discrete and KT. Whatever we have derived here for the digital controller. And then you have zero order hold. Somehow even though it is not completely continuous, but this is your actuating signal that is driving the plant or driving signal. Eventually you'll get the output. Now, how can we show this one in terms of equivalent transfer functions? So, oh, don't forget to give those. So we can also show them in this way. So basically the sampler will be there. Then you have your GD. Then you have your zero order hold, 1 minus e to the power minus ts. We already derived this one by s. Then you have your plant, say GPS, and finally the output. So deliberately, we haven't given the start things here yet. So this is our RS. This is our CS. Now here, your error is ES. After the sampler, we have a star S, where it is discrete. The digital is also discrete, so you better put a star there. The output that we are getting M star S is also discrete. And after the zero order hold and the DSC, then we have US, which is now analog, even though it is not strictly analog. And then you have your plant. So for simplification, we can just group them together and call it G of S. Okay, so how can we find out the pulse transfer function of this particular case? So simple. Since we have assumed that those two are grouped together under G of S, so we can easily write that 1 minus e to the minus ts by s into GPS will be our G of S. And what is our CS, or the output? CS is just multiplication of GS, which is a summation of those two. And you have GDS, which is start, and as well as our error signal, that is E star S. Okay, so now finding the pulse transfer function is relatively easy because of the fact that these two are already grouped, and this one is also star, this one is also star. Only the fact is that this GS is not star. So you just take a star Laplace transformation, and that will allow us to make it C star S equal to G, because only the one parameter is, the other side is not star. So you can factor out the other two, and eventually this is the thing that you're going to get. And now we just take Z transformation, and that will give you a CZ equal to GZ, GDZ, and EZ. So we know that the final output relationship that you're looking for is basically a relation between CS and RS. So for that, you can easily take the help that the fact that EZ will be equal to RZ minus CZ. Okay, so you just put this value into this equation and just do a bit of manipulation. Eventually, what you're going to get is CZ by RZ will be GDS, GZ, GDZ divided by 1 plus GD Z and Z. So this is your pulse transfer function of the closed loop system with the digital controller inside. So it's also relatively easier to do. So once you know how to do the thing, once you are in trouble, just use the stored Laplace transformation. It should be solving the scenario. And the last thing that we want to cover under this topic, that is, if you have a digital controller, digital PID controller, then how can we actually find out the pulse transfer function related to that one? Okay, so let's see what we have in the PID controller. From the classical PID controller that we know, pulse transfer function of a digital PID controller. Okay, so from the classical one, we already know that the output of the PID controller NT is multiplication of your error signal. And then you have 1 by Ti, that is integral part, integral time constant, et dt plus derivative time constant with dt by dt. So this is what we know from the classical control. Now, how can we convert this one into digital controller? So this is what we are interested about. Okay, so let's first of all discretize this equation. Discretize this equation. Okay, so discretizing implies, for discretizing, one thing we have to, one assumption that we are taking, that we are going to take the trapezoidal rule for the area under the curve or the integral part. So trapezoidal rule. Trapezoidal rule is going to apply here. And for this one, just the difference. Okay, so difference between two samples, and the time is very small, so it should be working as a derivative controller. So now, if we discretize, then what we have is m kt equal to k, error is just been discretized, so e kt. Then the error from, if it is up to kth sample, then we have to start. Trapezoidal rule is the bases, sum of the bases. And so if you have a trapezoid, something like this, the formula for area under the curve is, if this is your height, and this is your A and B, so the formula is A plus B, two base, average of the two base into height. So in our case, what we have is, we have sample signal like this. Okay, so our height here is basically T, and this is one base and this is the other base. Okay, so this is how we have to find out the integral. So up to kth sample. Okay, so because we are discretizing it for t equal to kt, so m kt equal to k e kt plus the integral part that we want to eliminate is by the trapezoidal rule for each of the sample. So the first, with the common t, or the height that we have, we're keeping it outside ti. So ti is from the formula, and this t is for the height between the k, because it is same for every sample. Okay, so t, always t in between. So then the first sample will be, the first average of the bases is E0 plus E1 by 2. The second one will be E1 plus E2 by 2, and up to kth sample, that means E k minus 1 t plus E kt. EKT by 2. So this is an integral part. Now the derivative part, TD by into D, what was initially we had is DET by dt. Now is the difference between the current and the previous sample, and that is EKT minus EK minus 1t divided by t. So you're just keeping the t here. Okay. So this is the discrete one. Now, how can we simplify this one? Okay, so the first portion is not bothering us. That is this one is not at all bothering us. It's just as it is. Now we're the third one will also not bother us that much. So, but how to represent this thing on the middle one? This is what we have to figure out. Okay, so now how can we do that? For that, we're just assuming that and the middle one, the integral part, can also be written as a summation. So EKT plus T by Ti summation of H equal to 1 to K E H minus 1 T minus E H T by 2 plus TB by T with EKT minus E K minus 1T. Okay, so to simplify this one, we're just assuming that if HT equal to this portion here, so that means E H minus 1 T plus EHT by 2. This is a function, and as you can see, if f equal to 0, now if you put every parameter here 0, then you're going to get the result 0. So this is the initial condition that we have. And now we can also write as a summation, like summation of h tends to 1 to h from 1 to k f ht, because we also have a summation there. So you can write in this way. And just notice the fact that the summation is not from 0, but we know that most of the calculation we have started is from 0, but this one's specifically starting from 1. So that is why you have to subtract one value later on. So you have to keep in mind. Okay, so we started from this equation, and then we have found difficulty with the integral part. So we're trying to simplify. So we'll come back to this equation again, inshallah. Okay, so now the Z transformation of summation of H equal to 1 to K e to the power H minus 1 T plus e to the power H T by 2 is same as summation of the function, because we defined that one as a function as H1 to KF HT. Okay, so we can already see that the summation of this one we have already seen from the chapter 2, specifically the example A24. That was summation was from h equal to 0 to k. Okay, so the first parameter is not present here. So that is why you have to subtract that first parameter from the solution as well. And eventually it was figured out that the solution was 1 by 1 minus z inverse. Just review A24 if you want, equal to fz minus the first item that is not present in our case, so you have to subtract that one. But luckily for us, we already have figured out this is initial value is 0. So what we get here is 1 by 1 minus z inverse fz. Okay, so this is what we already figured out. Now we have to keep in mind that the other thing that we had in the other side is this one, isn't it? So this parameter, if you take it into the z domain as well, so then what we are going to get, this is a delayed signal and this is the current value. So we can find that one basically z inverse plus 1 ez, okay, ez by 2. Okay, so basically we want to find out what is the value of fz, because we have to replace the value of the fz there, so we can easily figure out that. Okay, so our fz value will be simply whatever the error value that with that one we have to figure out. We have to add in that one. So hence we can write that z transformation of summation of h tends to 1 is from 1 to k error h minus 1 t plus e h t by 2 equal to 1 plus z inverse ez. We should not relate this one. This is isolated and that is coming from this one. Now we are relating this one here. Okay, so this one with divided by 2 into, so this parameter will be coming 1 minus z inverse. Okay, so this is what was our integral part. So integral part can be replaced by this parameter here. Okay, so now we put this one into that equation. Okay, so now this one. Okay, so what we find now here is mkt equal to k and 1 plus ty twice ti 1 plus z inverse divided by 1 minus z inverse plus td by t into 1 minus z inverse. And then you have your error multiplied with that one. So few steps has been kept in the book, so that is why the thing become a bit complicated. So and they suddenly actually converted it from frequency from the discrete domain to the time domain. Sorry, the Z domain. So that is why you have to be careful while you're transforming and escaping one or two lines. Okay, so now this is your equivalent pulse transfer function for a digital PID controller, but still we can do a bit of modification here. Okay, so if you do a bit of modification here, eventually what we are going to get is K1 minus T by twice Ti plus TD, sorry, it should be T by Ti by 1 minus Z inverse plus TD by T into 1 minus Z inverse. Okay, so this is your errors signal. Now, finally, what you can do that this is simply our constants. This is the integral part that is related to 1 by 1 minus Z inverse, and this is 1 into Z. So this is what is actually determining whether it is related to a derivative part, or if it is divided, then it is related to the integral part. So we can finally further what you can write is we can say that this particular portion can be written as Kp, the whole thing, k multiplied with this one and this one. There is Kp, and then Ki by 1 minus Z inverse, and then you have Kd into 1 minus Z inverse. So this is the final look of our digital PID controller. Okay, so don't forget yet the MZ and EZ. So finally, GDZ for the PID is MZ by EZ, and which is Kp plus Ki by 1 minus Z inverse plus Kd into 1 minus Z inverse. Okay, so this is how you have to do a bit of tweaking. Sometimes some of the complicated thing will be coming in the way, and where you have to use your intellect to figure out the solution of that one. So the proportional gain is given as K minus Kt by twice Ti. And interestingly, whether you have noticed or not, Ki, if you try to write Ki, the Ki is basically Kt by twice Ti. So, so 2 is not there. So, as you can see, this is your integral gain. So your proportional gain is half of the integral gain is also subtracted. So this is your half of the integral gain. So this is what you have to keep in mind. So K minus, you can also write Ki by 2. So in classical control, whatever the Kp, the gain of the proportional controller is, which is in digital controller a bit lesser than that. So you have to keep that thing in mind. And finally, Kd is Kpdi by T. Okay, so this is how you have to find out the pulse transfer function of a digital PID controller. This is velocity form. So different forms of PID controller is also available, velocity form and the position form. So whatever we have derived here, this one is position form. Position form PID controller. Digital, don't forget. PID controller. So the velocity form is also available. So that is your equation 357. So just have a look at that one, and corresponding figure is been given as well. Figure 330. So that's all for this lecture. So carefully try to solve those things. With there, sometimes they skip 1 or 2 lines. That is why you may get confused, but just practice a bit and it should be easier, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.